everyone. Today we're excited to introduce our project titled AI-powered mispayment detection tool. Going through the list of content, we're going to go through the introduction, problem statement, approach, background, methodology, dataset description, dataset pre-processing, data analysis, model selection, model evaluation interface, and finally with the conclusion. So imagine one missed loan payment. It might not seem like much, but for a bank or business, it can cause serious problems. Most current systems that check credit risk are slow and they're not always accurate. That's why we created the AI-powered mispayment detection tool, which is a smart system that helps predict who might miss the payments before it happens. For the problem statement, we know that people may not pay their loans on time, which can hurt the business money flow and the trust in actually their system. So old methods, they don't work well anymore because they can't keep up with the changes in the people's behavior or even the economy. So we need a better, smarter way to find the risks early and avoid big losses. That's why we came up with the solution to build a predictive tool using historical loan data to detect the patterns, forecast the mispayments, and improve credit risk assessment. The impact is going to have a lower financial risk, better loan decisions, higher profitability, and enhanced forecasting accuracy. For our approach, we're going to use 3 machine learning models, which is KNN, gradient boosting, multi-layer perceptron. So then we made up with a simple and easy interface so loan officers can quickly see who's at risk and make better decisions. So the approach actually is an application-based approach focused on real-world usability, a functional tool tailored for financial end users, and a user-friendly interface for easy prediction and interpretation, which enables faster and smarter loan approval decisions.
My name is Ala Al-Hajjaj and I will talk about background methodology and data description. In recent years, the rise in personal debt has made it increasingly important for banks and financial sectors to detect potential defaulters early. Traditional credit assessment methods like automated approvals or manual reviews often fall short. They can be biased and lack predictive power. Many early studies applied models like logistic regression, XGBoost, and LSTM. However, they often struggle with generalization, especially across different banks with varying approval policies. Most recent work has shown promising results using models like LightGBM, ANN, CNN, and chat-based explainable AI. Still, there is a clear gap. Few studies provide application-based tools that offer both visual analytics and model comparison for default prediction. Our project aims to fill that gap. The methodology we followed first starts with dataset, then EDA, followed by feature engineering and model selection, then training and evaluation the model, ending with application. Worked with a financial dataset acquired from Coursera for predicting default risk, using 255,347 training and 109,435 tests as a test set. However, the dataset containing client features such as credit score, income, loan amount, and interest rate. Initially, the dataset was highly imbalanced, meaning there were significantly more non-defaulters than defaulters, which could bias our model toward the majority class. To address this, we applied SMOOTH, an oversampling technique to balance the dataset, achieving equal classes distribution about 225,000 records for both defaulters and non-defaulters. We also performed extensive reprocessing, including one-hot encoding for categorical features and dropping high credentiality columns like loan ID to prevent overfitting.
Assalamu alaikum Fatima Joshi. To begin our exploratory analysis, we explored our numerical features, focusing on key variables like age and loan amount. From the describe function and box plot, we observed that both features follow a relatively symmetric distribution. For instance, the age of borrowers ranges from 18 to 69, which is consistent with the legal loan age. This suggests that the dataset reflects realistic borrowers' demographics. Loan amounts are also symmetrically distributed, with no extreme outliers, simplifying the pre-processing and indicating stable data quality. Next, we look at the target variables, whether a loan was defaulted or not. Originally, only around 12% of the records were defaulters, which caused a severe class imbalance. To address this, we used SMOT, which creates synthesis example of minority classes. After balancing, we now have equal representation around 225,000 records in each class. Moving to the categorical features like employment type, we applied 100 encoding during preprocessing. The distribution is relatively balanced across all categories, including full-time, part-time, and self-employed and unemployed individuals. This diversity helps the model to learn equally from all groups and prevent bias towards any single category. For outlier detection, we use both IQR method and boxplot. The result, no major outlier in key features like age and loan amount, so overall the data is excellent to shape for modeling. Next, we examined how features are related to each other using this correlation heat map. The good news is, no correlation is too strong. The highest is around minus 0.30 between age and default, meaning younger borrowers tend to default more. Finally, we explored which financial and demographical features are most linked to the defaults. In terms of employment type, the unemployment group had the highest default rate, followed by part-time and self-employed individual, and full-time workers had the lowest. For loan purposes, loans for businesses have slightly higher default rates than the others, for example, home loans. This helped us identify higher risk borrowers, provide for better risk management. And finally, looking at age, younger groups, especially 18 to 25, shows highest default rates, consistent with earlier correlation heat map. These insights help us to understand risk behaviors and will directly guide us in how we can train and evaluate our model.
I'm going to talk about the model selection and implementation, the random forest. So here the random forest is an ensemble learning, also it's a machine learning technique that builds up multiple decision trees and combines their results to improve the prediction. Also it's very effective for handling large data sets, similar to ours that we're handling. It has both numerical and categorical features. Also it's very robust to noisy data and can naturally rank feature importance. Also they are often used in like credit scoring, customer segmentation, and fraud detection. As to the XG boost, it's short for extreme gradient boosting. Also, it's very highly efficient algorithm. It's designed for fast and to make accurate predictions. Also, it improves the model performance by correcting errors from previous trees. Also, it has kind of built-in regularization, where it reduces the overfitting and supports parallel processing. Also, it's very commonly used in such credit risk analysis. Then the decision tree. The decision trees are very simple, very powerful. It's kind of a baseline that we used. Also, it creates like kind of easy to understand paths that can handle both numerical and categorical data without extensive like preparation. Also, they are very commonly used in credit approval systems, in customer segmentation, and also risk assessment. Light GBM, it's short for Light Gradient Boosting Machine. Also, it's a very high speed gradient boosting framework. Also, it's an ensemble learning model. Also, it's a leaf-wise tree growth strategy that reduces more loss compared to traditional leaf-wise methods. Also, it's very known for its low memory requirement and rapid training speed. It's very popular for real-time fraud detection and such utilizations. So here is the code that we utilized. Here we used shared pipeline to generate an accuracy for 3 ensemble models, which are XGB, Boost, Random Forest, and Light GBM. We started by loading the dataset, then we dropped unnecessary features, like splitting feature and targets, to default and non-default ones. Then we identified the column types, and we used transformers for encoding like the categorical and numerical features. Then we pre-processed them. Then we evaluated them and did some train and test split. Also, we generated lastly the classification report for them. The decision tree code is very similar. We created a pipeline, an individual one this time. Also, there were we utilized some transformers for it. Also, there were some splitting for the data and some training. And also, classification report was generated at last. At last, the model evaluation. Random Forest had the best accuracy and best overall performance for our task, the prediction task. Decision tree had the highest F1 score for determining non-defaulters and defaulters correctly. Overall, they do have very similar performance, but Random Forest gave the best balance. Here, the visualization of the model's performance. The XG boost gave best area under the curve, accuracy, HEM, and Random Forest and Light GBM, while decision trees gave the least, which was 0.88. Also, we created some confusion matrix to determine the true positives, true negatives, best recall, best precision, and so on. So they gave us really good numbers. Here, overall and all, you can see here the recall in XGP boost was good. It produced like strong default predictions. Random forest had the highest in precision. Decision tree was the strongest in recall, where it captures many defaulters. Like JVM was very good in precision. Also here we created bar charts for having the accuracy and precision to see it visually. As we can see here, it's very similar. However, the random forest gave us the best balance for our intended task. Thank you.
Hello everyone. So as the for interface demo, we build a simple interface that let the user to manipulate different features including age, credit score, employment, and so on. And eventually it allows the model to predict whether the user will repay or not, indicating the risk score and some tips.
Our main finding revealed that better data quality, better model performance. Smart as a method to balance the proposed dataset helps in improving the model's reliability, leading to achieved realistic results. Unlike earlier models like MLB, KNN, and gradient boosting performed poorly due to the imbalanced dataset. Another finding related to the importance of preprocessing. The pre-processing techniques that were applied include dropping high cardinality fields, encoding categorical features properly, and ensuring balanced data. It plays a critical role in models' accuracy and fairness. Another main finding related to ensemble models. Our experiments demonstrate that ensemble-based models are highly effective in binary classification like loan default prediction. In addition, the ensemble models outperform traditional methods.
In conclusion, the rapid growth of debt has increased the need for effective solutions to address defaulting clients. This project has introduced different approaches to balance and solve these issues. As a future work, we suggest to further explain the ethical dimensions of data-driven lending, particularly regarding bias and fairness in model predictions. Thank you for listening.